For our last session today, we're just going to practice some coding. So we're going to put everything we learned from yesterday to use in this task, predicting abalone age from physical measurements. So if you haven't already, please go to this website and open up this notebook. And so we can start by importing all the packages we need and reading in the data. And let's just take a look at what kind of data we have, right? So there are three choices for the sex of the abalone. It's male, female, and then infant. I guess they're not, they're indeterminate before some certain age. You have all these different measurements, like the length, diameter, height, the whole weight, the shucked weight. So all of these different measurements that researchers have made of abalones. And then there's also this final measurement of the number of rings. And apparently if you add 1.5 to the number of rings, then you'll get the approximate age of the abalone in years. And so our task here is to use all of this data, so numerical data here and also categorical data, to predict this numerical outcome, the age of the abalone. Okay. So the first exercise is to use this getDummies function from pandas, so that we can convert the categorical column into a one-hot encoding. So we talked about this yesterday. We actually manually wrote a function which performs this one-hot encoding. But here I want you to write, to accomplish the same task using this function. And I'll give you a minute to do that. I would suggest just seeing what this does to, for example, the categories. So, yeah, on this, use pd.getDummies on this. So you see we've encoded the sex as a 0 or 1, depending on what category we're in. So this is pretty general. You would want to do this for neural networks. For every categorical variable that you had, you would try to convert it to this. OK, so we have all of this data. So we have the one-hot encoding of the sex for every single abalone in our data set. And now I want you to use these two functions to replace this column with its one-hot encoding. And yes, you'll need to pass this as a second argument to df.drop. And I think all of the answers subsequently are hidden, so you can check if you got it correct. So I'll give you maybe 30 more seconds. So the first thing I would think to do is, since we have these categories, the one-hot encodings, why don't we just join that onto the existing data frame? So one-hot. And let's take a look at what the data frame looks like now. Oh, Right. I can't run it more than once. Okay. Right, so you see that we've actually joined these as new columns onto the existing data frame. And the second part, just dropping this column because we no longer need it. Let's make another cell. So I would just say dot drop axis equals 1. Right. And now you can see that once we've dropped that column, it disappears from the data frame, and we just have the one-hot encoding at the end. Okay, so we've made good progress here. So the next thing we want to do is, well, we want to predict this column, the rings column, using everything else in this data frame. So I want you to grab the column of the number of rings as y, and everything else is x. So I'll give you a minute to think about how you would do this using those functions we've seen already. df.drop, and also indexing into the array. Let's start with the easy one, kind of. It's what we're trying to predict. So I'm going to have to type this entire thing. And we can just check what it looks like. So if we go back to this, yeah, 15, 7, 9, 10. That's what we see here. And then in terms of x, well, we want every column except for that column that we just took out. So we can just write rings. Oh. I can copy this. And you will also need the axis equals 1. That tells you to drop a column rather than to drop a row, which is the default. And you can see we no longer have the number of rings. So that's great. We've separated our data sets into our inputs and our outputs. And there's this nice function in scikit-learn. So from sklearn import, dot model selection, import train test split. And you've heard the importance of splitting your test set or your data into training and test sets to show that your model actually generalizes. So we'll want to use this on x and y so that we can have at least a rudimentary test set to check our model on. And I never remember the order that you have to put this in. And so that's like a good tip for doing this in practice. You should look at the documentation or look at examples. So what this function does is it takes x and y. It takes 70% of them as the training set and the other 30% as the test set. And it returns you these 4 data frames, which have that split. And here I've written random state equals 0. That's so that if you run it multiple times, it gives you the same answer. But typically, you would want to do this if you're, for example, publishing your code for the analysis that you're doing. OK, so we can do this. And now we can actually make some simple models. This is going to be where we decide how we're going to predict our output from our inputs. So just as, first step, let's just write a sequential model with a single layer, linear. And then here I'm going to have to say length of x dot keys. So what this does is it gets the number of columns, and then we're predicting one number at the end, the age. So that's going to be a 1. So it's saying go from this many attributes to this many attributes using a single matrix multiplication. That's what a linear layer is. So we can run this. So we have our model defined. And I won't go through this, but this is how you would organize your data further if you wanted to do this training on multiple computers, for example. It's pretty straightforward. You have to define one of these data set types. And here I'm just doing some processing to store all the data as tensors, as torch tensors. And then you need to implement these two functions, these two methods for this data set, the length and the get item. But after you've done that, basically PyTorch handles everything else with iterating through your data set and distributing that among the different computers that you're using. So what I've done is I've just made data loaders for the training set and the test set, and they just look like this. In the training set, I'm saying every time we go through the entire training set, let's reshuffle the order of the entries. And here, so we come to how are we going to optimize this model? What are we going to optimize it for? And here I'm just asking you to use the squared loss. MSE is mean squared loss, or mean squared error. And the atom optimizer. So we talked about this yesterday. Given all of the functions' gradients with respect to the weights that we want to optimize, we use this atom optimizer to apply the gradients. So this is just to have a nice progress bar. So the loss function that we're using is torch.nn MSE loss. Okay, I might have to do that. I've already filled in the optimizer here. It's just atom, and you call it on all of the trainable parameters of this model that we defined up here. So what are we trying to optimize? Well, our loss function is going to be applied on what we predict compared to what was the true value of the age. So you can see here we're iterating over the batches in the training data set. So here are the inputs and here are the outputs. And for each of these, we're going to apply the model to the inputs. And this is going to be our prediction. This is, again, just to show the progress. And then just like we did yesterday, we're going to call the backward method on this loss. And then we're going to use the atom optimizer to step forward. So this backward method, remember, it gives you the derivatives for all of the parameters that this value loss depended on. Okay. I did not run this cell. It should work now. And I just chose an arbitrary 100 iterations to train. This is, in practice, something you'll have to look at the training curve and see how quickly it goes down. But you can see we're trying to minimize this loss with a single layer here. So it's almost done training. Okay, and then this, oh, that was the answer. And now we're going to just evaluate our model on the test set. So you can see I've replaced train loader with test loader. And we're going to store the results just in a list. You should usually call this, you're telling the model that you're no longer training it. And this is important for other kinds of layers that we didn't include. But from here, let's just evaluate our model on the xi. So actually, I don't even need yi here because I'm just evaluating the model. So you can use underscore, or it doesn't really matter what you use there for the variable name. Okay. And yeah. Okay. Whoops. There's also just some extra stuff that you need to call to convert this from a PyTorch array tensor into a NumPy array. Okay. Okay, there's our predicted results. You can see the correlation coefficient, which I calculated here, is 0.5. It's not great, but it does look pretty convincing that there's probably some kind of positive trend here. You'll notice that each of these, so along the x-axis is the true age, and the y-axis is our model's prediction. But you'll notice that along the x-axis, there's not points scattered between these specific values. And that's because when we counted the number of rings, or in our input, our output, these were whole numbers. So the true age is always going to be a whole number, whereas the neural network outputs a continuous number, right? Okay. So we can go back now and apply some of the advancements in neural networks that have been found. Jen mentioned residual connections earlier today. There's also all of these different methods to regularize or prevent the model from overfitting. So there's dropout. Dropout, what it does as a layer is it takes your data and it randomly sets some of the values to 0. So you're introducing noise into the training process. And this is a really efficient way to introduce that noise and prevent you from overfitting. There's leaky ReLU. This is a modified version of the typical activation function that was originally used. They used to use hyperbolic tangent because it looked sigmoidal, or a ReLU, rectified linear unit. And that's basically, it's basically a line that's horizontal up to 0, and then it starts going up as x. So it's piecewise linear, but there's non-linearity introduced because of that condition, that your x has to be greater than 0. And then there's batch normalization. There's a lot of different types of normalization. And this is to prevent the weights from going off to infinity when you're doing the training. We saw an example of where the loss function was actually unbounded, like log z, the derivative is 1 over z. And at some point, it shoots off to minus infinity. And this is one way you prevent that from happening when you're training your models. So I'll just write a quick model that you might see. So let's start with a linear layer. And actually, let's import all of these from torch.nn, import linear dropout eqrelu. So remember what we said here, it takes that many inputs and gives you, let's say, 128 outputs. Let me move this up. Right before that, we might want to add a dropout layer. Right after that, we'll want a leaky RLU. And then maybe also before this, we might want a batch norm 1D. OK. And then what I'm going to do is just add a few more layers. So let's have a 128 by 128 layer here. Remember that these numbers have to match. Like the last number of this one has to match the first of this one. And that's just to do with how the shapes fit together. We can do another batch norm here. Leaky RLU. And then for our final layer, let's include all of these elements again. And we're going from 128 to back to a single number. Right. OK. Let's see if that works. It doesn't. And that's because I forgot a comma here. And number of features, so I think I need this. 128. 128. Length of x dot keys. OK. So it's always impossible to type everything correctly very first time. So you have to do a lot of debugging. OK, so we have a model defined here. And let's go back and retrain our model. So we can check the loss here. Looks like it might be a little bit lower than last time. And then we'll go here and run this cell again to evaluate our model on the test set. So I'll queue that up. OK. And now we'll plot it again. OK, that's bad. I think because one of these, let's see what I wrote before. Right, I think it's because I switched the order of batch and dropout. So the order does matter. You have to be a little careful. I can just run this. And let's do the training again. Train. And then results, and then we'll want to visualize it. OK. And by the way, you can make this faster with the GPU. So you would do this. But you would need to change the code a little bit so that it works on GPU. OK, we're almost done. OK. Huh. Is it because OK, I see what. So actually here, when I was getting the predictions during the training, you have to reshape the arrays so that it does like point-wise comparisons rather than, this is a case where the array broadcasting we talked about yesterday can screw up your results. But if I do that, they say you should never do live coding when giving a lecture because something will go wrong. And then you spend an hour trying to fix it. That's why I typed out all the answers this time. OK, so that's done training. OK, great. Correlation coefficient 0.76. So we went from 0.5, it wasn't actually supposed to be that low, it was probably around 0.6 to 0.76 just by adding a few additional layers. And there's not really like any principled way to decide how many layers you need or how many hidden units you need. It's a lot of trial and error. What's helpful is looking at what architectures others have used before in papers. And just a quick note, the initial model that we have, the linear model, I just had one linear layer, and that corresponds to least squares linear regression, so ordinary linear regression that you might be used to. And actually, that form of linear regression has a closed form solution. So if you take all of the features like we did, so that was x, our x, and you append a column of ones onto it, then the linear model that best fits, so the coefficients, is actually this complicated matrix expression. OK, but we've kind of gone through how you would go from just raw data of different types, categorical and continuous, and we've predicted a continuous outcome. And so you'll find that a lot of data sets kind of fit into this description, where you're trying to predict a continuous outcome from mixed variables. There are methods to predict categorical outcomes, and it's kind of the reverse of one-hot encoding. It's actually what Jan showed to you this morning with the softmax. So that would be your final layer. So I hope you found this helpful. You can try this on other data sets you might have lying around in the lab. Just try to predict one of the variables from all the others. Yeah. And that's going to be the end of our machine learning workshop today. So thank you for coming. We'll be sending out like a link with all of the recordings once they're finished, and all of the code, including Professor Tropshaw's code. All right.